Welcome to video number 2 for the AP Chemistry Bootcamp. And we are still on the topic, not so much chemistry, but just numbers and calculations. And this particular video is just going to be dedicated to talking about significant figures. And so in chemistry, we'll do laboratory experiments in which we make measurements. You will also have a lot of calculations and problems to do in which numbers are given to you that represent measurements. And so in those cases, then you have to be able to determine how many significant figures those numbers have, and then how to manipulate those things in calculations. So here we go, significant figures. How many digits do I need? Well, so there are basically two kinds of numbers when we're talking about significant figures. There are exact numbers. These are defined numbers. So for example, that there are 3 feet in a yard is a defined, so they're exactly 3 feet in a yard. There are exactly 12 inches in a foot. There are exactly 100 centimeters in a meter, etc. And so those have exact values. They're not determined by measurement, they're determined by definition. There's one type of measurement that also gives us an exact number, and that would be a measurement made by counting. So for example, if we asked how many people were in the room, and we counted off that there were 9 people in the room, that's an exact number because there's really no fraction of a person if you're talking about how many people are here. So defined numbers, measurements made by counting, those are exact numbers. Inexact numbers are most measurements that we make. In other words, determining the mass of something, or determining the length of something, or determining the wavelength of a particular light, or measurements that we make, volume. These are all measurements that require a certain amount of estimation because there's always some limit to the sensitivity or precision of the instrument that we're using to make those measurements. All right, well, what are some examples of each of these types of numbers? Some examples of exact numbers. I've already said that 1 yard is equal to 3 feet. An hour is equal to 60 minutes. 1,000 meters equals a kilometer. These first 3 are all examples of defined numbers. Now here's an exact number that's actually a measurement. There are 17 pennies on my dresser, but because, again, there's no such thing as a part of a penny on my dresser, that's an exact number because I didn't make it by measurement in the sense of sort of estimating. I made it in the sense of actually counting them. And here's something that you may not realize is an exact number, but the inch is now defined in terms of the metric system. It is considered to be exactly 2.54 centimeters. What would be some examples of inexact numbers? Well, these would be measurements that involve some sort of limits of detection. So for example, if I get on the scale and it says that my weight is 187.6 pounds, that's not exact because if there was a more precise scale, it might be able to tell me to several decimal places. And so there's some point at which the measurement exceeds the precision of the instrument, and so that would be an example of a measurement that gives you an inexact number. The temperature is 92 degrees Fahrenheit. I added 50.0 milliliters of water. This board is 8 feet long. I inflated the tire on my bicycle to 110 psi. These are all examples of measurements whose precision is determined by the level of sensitivity of whatever instrument I'm using to make the measurement. So here's another example of something that might happen in a laboratory. I've got we'll cut away part of a graduated cylinder here, and I've got a blue liquid in it, and I'm trying to figure out how much I've got. And so just as a general definition, or just a general guideline, whenever you're trying to determine the volume of a particular liquid, you're looking at the bottom of that little curved thing, which is called the meniscus. And so the question is, how much liquid do I actually have in that container? Well, you know that we've got more than 35 and less than 40, because you can see that it's between those two graduations. But then this cylinder is even more sensitive because it's got a graduation every 1 milliliter, and so we know that it's actually more than 36 and less than 37. But how much? Generally, we're going to have to guess at what the last digit is. And so I could say that that represents 36.4 milliliters. Somebody else might think that that represents 36.5 milliliters. In both of those cases, the 4 or the 5 is meaningful because it tells us that it's sort of somewhere halfway in between 36 and 37. And so we would include that. But since we can't agree on whether it's 0.4 or 0.5, we certainly couldn't put any other digits beyond a 0.4 or a 0.5. So any measurement that's made by a method other than counting contains a certain number of significant digits or significant figures, the last of which is meaningful but uncertain. And that's what I was just saying before. We can agree that it's 36 point something. Whether it's 36.4 or 36.5 is up for debate. But it is useful to have that 0.4 or 0.5 there, because that actually tells us that it's, pretty much right in between 36 and 37, and it's not 36 and it's not 37. We can be more precise. Now, one of the things that'll happen a lot in solving problems is you'll be presented with numbers, and you'll need to determine that represent measurements or represent numbers with a limited number of significant figures, and you need to figure out how many significant figures that number has. And so, and the way that we deal with this is by looking at two types of digits. There are non-zero digits, which is anything 1 through 9, and then there are zeros. And so when you're trying to figure out how many significant figures a particular number you're presented with has, non-zero integers or non-zero digits are always going to count. So every non-zero digit you see in a number presented to you is going to be a significant figure. Then there are 3 types of zeros, and depending on the type and some other factors, whether determines whether or not they're significant. So the first kind would be called leading zeros, and an example would be these zeros in this number here, 0.0025. Leading zeros in a number like that are never significant figures, because they're just placeholders. They're just telling you basically what the power of 10 of this number is. So the only 2 significant figures in this number are the 2 and the 5. So this has only 2 significant figures because the zeros are simply telling you where to position the decimal point in that number. And we can actually kind of prove that or demonstrate that to ourselves by writing this number in scientific notation, which becomes 2.5 times 10 to the minus 3, and now it becomes clear that the coefficient only has 2 significant figures. Captive zeros, or zeros that are in between non-zero digits, those are always significant because they are part of the number itself. So for example, this number 1.008 has 4 significant digits or 4 significant figures because the 2 zeros are in between the 1 and the 8. So captive zeros, or zeros that are in between non-zero digits, are always going to be significant. And then there are what we call trailing zeros, which is zeros that come after the last non-zero digit. And the question is, well, are they significant, or are they just there again to position where the decimal point would be, or where the sort of zero place is? It depends on whether there is a decimal point present. Okay, so for example, there are two representations of the number 100 here. There's 100, and that's the end of it, and then there's 100 with a decimal place. And by convention, the fact that there is a decimal place there is telling you that all the trailing zeros are significant. And so that top number only has 1 significant digit, and we can write that in scientific notation as 1 times 10 to the second. The bottom number has 3 significant figures, and so because these zeros are significant, we would write it in scientific notation as 1.00 times 10 to the second. Well, what's the difference between them? really. They're both 100, right? But in this case, we're saying, well, we know it's 100 versus 0 or 200, where in this case, we're saying we know it's 100 versus like 101 or 99. So the number of significant digits is telling us the precision to which we know that number. And then exact numbers have infinite significant figures. So if I just back this up to where we gave some examples of exact numbers, 1 yard equals 3 feet. That's 3.000000 on out to infinity. So because it is exactly 3 feet and exactly 1 yard, then it has infinite significant figures. Okay, let's get back. Here's a little bit of significant figure humor. You can pause the video and watch and take a look at this if you'd like. Otherwise, let's move on. So the main thing really is once you've identified that a number is an inexact number and how many significant figures it has, that influences, when it comes to manipulating these numbers and calculations, how you report your answer, how many significant figures you report your answer to. So when you multiply two numbers together or divide, then you're going to report your answer to the same number of significant figures as the number that you were in your calculation that has the fewest significant figures. So for example, if we know 4.56, if we take 4.56 and we multiply that by 1.4, your calculator is going to show you that that says 6.384. But because we only know this number to 2 sig figs, then we really can only know our answer to 2 significant figures. And so we would take this and we would round it from 6.384 to 6.4. If I'm going to add or subtract, now it's different. Instead of talking about numbers of significant figures, we're talking about numbers of decimal places. And so we are going to add this up, and then we're going to round it to the same number of decimal places as the least precise measurement in the sum. And so if I add 12.11 to 18.0 to 1.013, I get this number on my calculator, 31.123. But because I don't know anything past the 0, the first decimal place here on this 18.0, these numbers are kind of meaningless because there could be something out here, we just don't know what it is. And so trying to say that the 2 and the 3 are now significant when we don't know what is beyond the 0 here, we can't do that. So we're going to round it to the first decimal place because this number only has 1 decimal place, and our answer is going to be reported as 31.1. Okay, what about rules for rounding? Well, one thing you don't want to do is to do intermediate rounding. In other words, you should look at a problem because you will often get problems that have several operations in them. And you don't want to keep rounding every time you do one operation because you will start to get rounding errors by doing that. So what you want to do is carry the calculation all the way through to the end with all of the digits that your calculator is giving you, and then go back, figure out how many significant figures your answer should have, and round it at that point. And when it comes to rounding, if the first digit to be removed is less than 5, then you're just going to keep that the same. So in other words, if we're removing the first digit and only digit we're going to remove here is this 3, since it's less than 5, we just scrub it off and the number in front of it, the other 3 remains the same. If the first digit that we're going to remove is equal or greater than 5, then we round up the previous digits. So if I take 1.36 and round that to 2 sig figs, because the 6 that I'm removing is greater than 5, then we round the 3 up to a 4. So here are some examples of some things that can give people confusion, because what I've done here is list a series of numbers that all have 3 significant figures. You'll recall that leading zeros are never significant. Zeros between non-zero digits are always significant. So this one has 3 significant figures, the 3, the 0, and the 7. You'll recall that trailing zeros are not significant if there is not a decimal point. And so because there is no decimal point here, these 3 are simply placeholders to get us into the hundred thousands place. And so this number only has 3 significant figures, the 4, the 2, and the 8. This one has a decimal point, and so all numbers are significant, the 8, the 1, and the 5. And again, now here's an example of a number with both leading and trailing zeros. Leading zeros, as you'll recall, are never significant, but because I have a decimal place, that makes my trailing zero significant. And so if I write all of these in scientific notation, you can now see that they all have 3 significant figures. 3.07 times 10 to the minus 3, 4.28 times 10 to the 5th, 8.15 times 10 to the 0. That's a form of scientific notation we'll essentially never use, but it's just telling you that that number has 3 sig figs. 6.90 times 10 to the minus 2. Okay, here are some sample calculations for you. So you can go ahead and pause the video, work these, and then turn it back on, and I will give you the answer. Okay, so when you add 334.540 to 198.9916, this number, this is an addition or subtraction operation. So this number has 3 decimal places. This number has 4 decimal places. So you're going to round your answer to 3 decimal places, 533.532. If I'm taking 34 grams and dividing by 10.1 milliliters, now it's a multiplication or division operation. And so I'm going to round my answer to the number of significant figures that is equal to the measurement with the fewest significant figures. So this measurement has 2 significant figures. This one has 3. And so I'm going to round my answer to 2 significant figures. Here is a multiplication operation. And so again, I'm going to round my answer to a number of significant figures that is the same as the measurement with the fewest significant figures. As it turns out, both of these measurements, 44 meters per second and 20 seconds, because this has a decimal place, that has 2 sig figs. This has 2 sig figs. So my answer is going to have 2 sig figs. And the way I indicate that that 0 is not significant is by not putting a decimal place there. And then finally, a subtraction. Again, we are talking about not numbers of significant figures, but numbers of decimal places. This number has 4 decimal places. This number has 2 decimal places. Therefore, I'm going to round my answer to 2 decimal places. Okay, I think there are a couple different worksheets with the significant figure practice for you to work on with this. So enjoy yourself, and we'll see you on the next video.